Did you know that there is a secret unlock for the FRQs in the AP Physics exam? I'm not even joking. Of course, you need to know physics and all of physics to do well on the FRQs. There is a secret code behind how they put together the FRQ questions. There are some specific skills they're looking for, and they actually structure the questions the same way every year. There is going to be 4 FRQ questions, and they even have names, the 4 kinds of 4 names, and they even have the same way they structure the questions every year. So you can actually know what the 4 kinds of things they want you to do are, and you can know the journey of each question beforehand. The first kind of question is called mathematical routines. Here, what they're wanting is for you to use mathematics to derive an expression. So there'll be some question about a certain kind of physics principle, and you always need to begin by writing down the equation of a physics principle, and then use that to, with variables, derive an expression. A student has a cart of mass mc and a block of mass 1 over 5 mc, as shown in figure 1. At time t is 0, the cart is moving right across a horizontal surface with constant speed vc. The student releases the block from rest. At t equals t1, the block collides with and sticks to the top of the cart. The block does not slide on the cart. At t equals t2, the block cart system continues to move to the right with constant speed. And the main idea for this question is momentum. So we're going to be thinking about the conservation of momentum law. Part A, question 2, says this. Derive an expression for the speed Vf of the block cart system after time t equals t2 in terms of mc, vc, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle. We need to use the law of conservation of momentum. One way to write that is the initial momentum is equal to the final momentum. So the initial momentum is just the mass m times v, and then the final momentum is the mass m plus 1/5 m times vf. So that's all the variables they've given to us. So we just have to rearrange these numbers and have an expression for vf. I get m times v equals 6 over 5 m times vf. I can cancel the masses. The question wants us to derive an expression for vf. So I need to write vf equals something. So vf equals 5/6v. That it's slightly smaller by a factor of 1/6 compared to the initial velocity. Notice that in this expression, there's none of the mass dependence. So that comes out of the formula. So this is an example of deriving a mathematical expression, and it's the key skill for the mathematical routines thing. There's actually some other parts to it, and there's a journey you'll go through every time. I'll delve deeper into this journey of question 1, mathematical routines, in the video. You can find the link for that below. Let's look at the second kind of FRQ. The second kind of FRQ is called translation between representations. What's a representation? The idea is that in physics, we'll have some kind of situation, and there's different ways that we can represent this. The most common way we represent things in physics is with diagrams and equations. But there's a number of key representations that you should have studied in your AP Physics course that they'll expect you to be able to produce. These will include a free body diagram, an energy bar chart, and motion diagrams, and various graphs. So each of these kinds of tools or representations is a different lens on what's going on. Let's look at an example. A block of mass m is released from rest at position x is 0 near the top of a ramp. The ramp makes an angle theta with a horizontal. The block slides down the ramp with negligible friction. At x equals 8d, the block makes contact with an uncompressed spring with spring constant k. The spring is then compressed, and the block momentarily comes to rest at x equals 12d. Figure 1 shows the instance when the block is x equals 0, x is 6d, and x is 10d, respectively. Figure 4 shows an energy bar chart that represents the kinetic energy k of the block and the gravitational potential energy Ug of the block Earth system, and the spring potential energy U Draw the shaded bars that represent K, UG, US to complete the energy bar charts in figures 2 and 3 when the block is released from rest x equals 0 and when the block is x equals 60 respectively. But the key idea here is we need to do an energy bar chart, which is one type of representation. Here the block has different kinds of energy. At the beginning, it has no motion, it just has potential gravitational energy, and then it begins to move. Before it strikes the spring, it's going to have a mix of kinetic energy and spring energy, and then once it compresses the spring all the way, it will have no more kinetic energy, no more potential gravitational energy, but only spring energy. Here are the bar charts for the 3 moments, and they've given us the energies at the third one. So if we look at that chart, we can see they've put the energies at specific numbers, and we've got to pay attention to what those numbers are. So if you look, the kinetic energy is 7 E naught, the potential gravitational is 2 E naught, and the potential spring energy is 3 E naught. So that means we can find the total energy is going to be the 3 added together, and I'm going to get 12 E naught. So that's great. So the law of conservation of energy says the total energy is always going to be the same in any situation, even if there's different kinds. So I just need to make sure that when I draw these bar graphs, they're always going to total up to 12 E naught. We think about the first one at the very beginning, there's only one kind of energy there, which is going to be the potential gravitational. There's no motion, so no kinetic energy, and no spring compression, so no spring energy either. So it's all potential gravitational energy, and I just need to write this going to be 12 E naught, the amount of energy. I draw a little line to represent the other two, or 0. Now the next one is a little more complicated, but I just need to figure out what kind of energies are at x equals 6d. Now there's no spring compression, but there's going to be a mix of potential gravitational energy and kinetic energy. And I just got to calculate what the potential energy is going to be. If we think about the block sliding down, at 0d it's 100% potential energy, and at 12d it's going to be 0 potential gravitational energy. So in the middle, at 6d, we're going to have 50%. So the potential gravitational energy is going to be exactly 6, which means the rest of it has to be kinetic energy. So they're both going to be 6. The block has not hit the spring yet, 0 spring potential energy. Okay, so here is an energy bar chart representation. These questions can actually be worth quite a lot of marks, even 5 marks. This question has another different kind of representation, which is sketching a graph. Figure 6 shows a graph of the energy of the system as a function of the position. Sketch and label a line or curve that represents the total mechanical energy. So I'm not going to do these questions, but this sketching a graph is another representation. Again, there's actually more components to this question. There's a journey that is a set journey they'll go through every time, and the full breakdown of that will be in the next video. The third kind of question is called experimental design. Here, they're wanting to see if you understand how physics principles will be worked out in reality with an experiment. And this question has a very clear journey, a path that you will follow every time. And there are 4 steps. The first step is to describe an experiment. So there'll be some topic and you have to talk about what that experiment is. Second, you'll have to describe how to collect data. So you need to be thoughtful about the way that you would organize the data to plot a graph. Third, there'll be some data and you'll need to plot that data on a graph and find a line of best fit. And fourth, you'll need to calculate a variable. Students are investigating balancing systems using the following setup. Students have a spring scale of negligible mass that is fixed to one end of a uniform stick. The center of the meter stick is attached to a stand on which the meter stick can pivot. There is a hook of negligible mass fixed to the top of a block M naught. The hook can be attached to the meter stick through one of the small holes in the meter stick, as shown in figure 1. Students are asked to take measurements that will allow the students to create a linear graph whose slope could be used to determine the mass m naught of the block. Describe an experimental procedure to collect data that would allow students to determine m naught. Include any necessary steps to reduce experimental uncertainty. So in part A, you have to describe the right steps to create an experiment. B, describe how the data collected in part A would be graphed and how that graph would be analyzed to determine M naught. To figure out what the right way to graph it is, you've got to do a little bit of equations. So let's do a basic equation for this one to show. It's going to be a balanced torque with rotational equilibrium. Well, let's write down the torque formula. We say torque counterclockwise equals torque clockwise. So here's the force of gravity with the distance that we're changing. So that variable is going to be like a independent variable that we're inputting or outputting a different force, spring force. That force is going to change. 0.5 is the distance it gave us on the graph there. So we can rearrange this. We'll put mg in for fg. And basically, we want to make it like y equals mx plus b, where d is our x, fk is our y. So what's the slope going to be? We just have to move this 0.5 number. So if we were to do a linear graph with d as the x and the force spring as the y, we would get this thing there. That's going to be the slope. All right, that's part B. So you want to say I would plot the distance on the x and the force on the y, and I would get a linear graph with a slope. And here's the equation for the linear graph. Part C gives a connected, similar question, but not quite the same, and it gives us some data. And we're going to be expected with this new part, this new thing, to plot this data and calculate something. Again, this is an overview. I just want you to understand the 4 kinds of questions. And if you want a deeper dive, I'm going to have a video on each one of them. The 4th kind of question is qualitative, quantitative transitions. Well, what the heck is that? What is qualitative? What is quantitative? So qualitative is where we talk about qualities. And the idea is we're going to use words and descriptions and English rather than equations. Quantitative uses quantities. That is, we're going to use numbers and variables and equations and algebra and math. And in physics, we need both these kinds of descriptions. The first part will have a question, and you have to do qualitative analysis. So describe what's going to happen with physics just using words and not using equations. In the second part, B, it will say derive some expression. That's quantitative. That's using the math. And then in the third part, we're going to put them together. So just words, then the math, and then say, do they connect somehow? Question 4. In scenario 1, a swimmer holds a block of mass m at rest in a tank of fresh water. With density rho, as shown in figure 1, the block is released and accelerates upwards with an initial acceleration a1. In scenario 2, the swimmer holds the same block at rest in a tank of salt water with density rho2. Rho2 is greater than rho1. The swimmer again releases the block accelerates in the acceleration now 2 upwards. So A, indicate whether a1 is greater, less, or equal to a2 by answering this, and justify your answer in terms of all forces exerted on the block in each scenario. Use qualitative reasoning beyond referencing equations. So qualitative reasoning, what does that mean? Don't use equations, use words, use the physics ideas. So what's going on here? We've got to say that there are 2 forces. There's a force of gravity down and a buoyancy force upwards. The net force clearly is upwards, so the buoyancy force is greater than the gravity force. So far so good. So the buoyancy force is related to rho, the density. When there's a higher density, there's going to be a greater buoyancy force, which means for the salt water, the buoyancy force upwards is greater and the acceleration upwards is greater. So we say A1 with the normal water is going to have a smaller acceleration than A2. So using words just like these is how we answer this justify with qualitative reasoning. Use English words, not equations. In part B, we'll use the math. Consider the general case where a block of mass m, volume v, is completely submerged in a fluid of density rho. Starting with Newton's second law, derive an expression with the initial upward acceleration a of a block where the block is released from rest. Express your answer in terms of m, v, rho, and physical constants as appropriate. Here, we're going to do like we did in question 1, some math with variables and come up with an expression, a math expression. And C is where we connect them. Indicate whether the expression for the acceleration A you derived in part B is or is not consistent with the claim in part A. Briefly justify your answer. So you're going to talk about the math you did in part B and say how it supports what you said in part A. And that's how question 4 works. So now you have the keys to the kingdom. You know the secret code of the FRQ questions. I'm going to continue to do one of each of the kinds of FRQs to show you how they work out in more detail. But for you to feel like a master of this topic, you're going to need to do practice questions. I highly recommend you get a resource like the Princeton Review AP Physics Exam Prep Guide, which has many questions, including FRQ questions, for you to practice.